Hey everyone, and welcome to The Explainer. So, have you ever actually stopped to wonder how a modern computer, which, if you really think about it, is basically just a machine made of sand, wire, and electricity, can pull off unimaginably complex calculations, process mountains of data, and literally drive cars? Well, it all boils down to logic. Specifically, simple, binary, true or false logic. Today, we're going on a pretty captivating journey. We're going to explore how incredibly simple declarative statements built the foundational rules of mathematical reasoning and how those ancient philosophical rules evolved to actually power the digital circuitry of every single modern computing machine on the planet.
All right, let's take a super quick look at our roadmap. We are covering 1. The foundation of reasoning, 2. Anatomy of a proposition, 3. Combining ideas, logical operators, 4. Conditional statements and contracts, 5. Visualizing logic, truth tables, and finally, 6. Logic in the digital age. Let's dive right in.
Section 1, the foundation of reasoning.
To really wrap our heads around this, we actually have to travel back over 2 millennia. We literally owe the Greek philosopher Aristotle a massive debt of gratitude for systematically developing the rules of propositional logic over 2,300 years ago. Aristotle, the guy who famously tutored Alexander the Great, laid down these incredible, systematic treatises on logic. He realized that to truly understand mathematics and philosophy, we needed a rigorous, bulletproof system to construct correct arguments. His work on the propositional calculus, which is just the mathematical framework for statements of fact, literally laid the groundwork for the entire digital age we're about to discuss today.
Moving on to Section 2, Anatomy of a Proposition.
So, the absolute crucial point here is that a proposition must be a declarative statement. It has to declare a fact. And most importantly, it's got to pick a lane. It must have a definitive truth value. It is absolutely either true or false, and it can never ever be both at the same time. In math, we usually just represent these statements with simple little variables like the letters P, Q, or R. And this brilliantly illustrates the exact difference. Take the statements Washington, D.C. is the capital, or 1 + 1 = 2. These are completely valid propositions. They state a fact, and we can definitively say, yep, they're true. Now, even a statement like 2 + 2 = 3 is technically a proposition. It just happens to have a truth value of false. But look at the counterexamples. What time is it? Well, that's a question, not a declaration. And x + 1 = 2 is totally up in the air. It's neither true nor false until we assign a specific value to that x. Therefore, those simply don't qualify as propositions.
Section 3, Combining Ideas. Logical Operators.
Fast forward from ancient Greece all the way to the 19th century. In 1854, a brilliant English mathematician named George Boole published his famous book, The Laws of Thought. Boole was actually largely self-educated, overcame massive financial struggles, and yet he gave us the exact mathematical tools we use to connect existing propositions into brand new, compound propositions. And we do this using what are called logical operators. Boolean introduced a few absolutely essential operators. First up is the conjunction, which we simply read as and. If we combine 2 propositions with an and, the new compound statement is only true if both individual parts are true. If even one single part is false, the whole thing crashes down and is false. Next is the disjunction, or. Now, this is an inclusive or. That means the compound statement is true if at least one of the parts is true, or, hey, even if both are true. Now, a great real-world example of a slightly different operator, the exclusive or, is a restaurant menu. We use the inclusive or a ton in logic, but in everyday spoken English, we actually usually mean exclusive or. Just like a menu that says soup or salad comes with an entree. We all know the drill. You get the soup or you get the salad, but no way are you getting both. One must be true and the exact other must be false. Looking at the truth table for the exclusive or XOR, as it's really often called in the biz, we can visually map this whole thing out. Notice the top row. When proposition P and Q are both true, the exclusive or outcome is strictly false. It is only true in the middle 2 rows, right, where exactly one of the propositions is true and the other is false. It's essentially a perfect mathematical representation of our soup and salad rule.
Moving right along to Section 4, Conditional Statements and Contracts.
A highly intuitive way to really understand a conditional statement is to think of it like a politician's contract with the voters. If I am elected, okay, that's our hypothesis, then I will lower taxes, and that's the conclusion. So when is this contract actually broken? Well, if the politician doesn't get elected, you obviously don't expect them to lower taxes, so the statement isn't technically false. The only way this pledge is genuinely broken, making the conditional statement logically false, is if the politician is elected, meaning the hypothesis is true, but they completely fail to lower taxes, making the conclusion false. Literally every other scenario mathematically results in a true conditional statement.
And this brings us to a super common trap in logical reasoning. We can manipulate a conditional statement into three related forms: the converse, the inverse, and the contrapositive. But, and this is a big but, you must remember that only the contrapositive always holds the exact same truth value as the original statement. If the original is, if it is raining, the home team wins, the contrapositive flips and negates both sides, becoming, if the home team does not win, then it is not raining. They mean the exact same thing in logic. Assuming the converse, like if the home team wins, it is raining, is logically equivalent is honestly one of the most common errors in reasoning out there.
Section 5. Visualizing logic, truth tables. Because propositional logic can get highly symbolic and visually complex really fast, we need a reliable, structured way to map out these combinations. Truth tables become absolute lifesavers here. But before we map them, we need some ground rules. Just like the order of operations in basic math, where you always multiply before you add, logical operators have a strict hierarchy of precedence. It tells us exactly which part of a compound proposition to solve first. The negation, or not, always goes first. Then the and, followed closely by the or. Conditional if-then statements and if and only if statements had the lowest precedence. Keeping this order in mind is absolutely critical for building accurate truth tables.
So let's evaluate a large compound proposition. The real beauty of a truth table is that it lets us break down the complexity column by column. We start with our base variables P and Q. Then we apply our precedence rules. We calculate the negation of Q first. Then we tackle the terms inside the parentheses, the or statement and the and statement. Finally, we evaluate the overall conditional statement. By doing this step by step, truth tables allow us to perfectly visualize every single possible outcome of a complex argument, leaving literally zero room for ambiguity.
And finally, Section 6, Logic in the Digital Age. The absolute critical bridge between ancient human philosophy and modern computing was built in the mid-20th century. In 1946, a brilliant statistician named John Tukey, who, by the way, also helped invent the fast Fourier transform, coined a brand new term, the bit. It's a clever portmanteau for binary digit. Tukey gave us a way to mathematically bridge the abstract human logic of Aristotle and Boole with the physical electronic circuitry that was being rapidly developed at the time. And this simple table, this represents a monumental leap in human history. It shows the direct, one-to-one translation between propositional calculus and computer science. The logical truth value of true just becomes a 1. The logical truth value of false becomes a 0. These form our Boolean variables. When a computer processes information, it is quite literally evaluating millions of these propositions, checking if they are true or false, using bitwise OR and XOR operations. The rules of logic specify the meaning of these mathematical statements, and that logic is the undeniable basis of all automated reasoning.
Which brings us to a really fascinating conclusion. We've traced the lineage from philosophers debating in ancient Greece to the processing chips sitting in your smartphone right now. Knowing that computers now use these exact digital building blocks to construct their own mathematical proofs and even pioneer artificial intelligence, we really have to wonder, just how far will automated reasoning evolve in the future? What boundaries will these simple true and false statements allow us to break next? Thank you so much for joining me today on this explainer through the logic that powers our world. Keep questioning, keep learning, and I'll see you on the next one.